What I said before about the stereospecificity of this reaction can be illustrated very nicely in this reaction here. And let's say that you have carbon atom attached to a methyl and ethyl that is there in the back, ethyl, and we have the hydrogen that is going to be abstracted by the base. And then the other carbon atom, let's say that you have a methyl in the back there, CH3 in the back, and then in front here you have, let's say you have an isopropyl group, and then you have the bromine, the leaving group there. So then here we will have the base that is abstracting this proton. Simultaneously, we will form a carbon-carbon double bond, and we will have departure of the bromine. So what will be the consequence of that? Let's figure out the chirality that we have, the configuration that we have on each one of those chiral carbons. So the one on the left, so we will have the big chunk of molecule followed by the ethyl, followed by the methyl. That will be the order of priorities. And so that will make it R configuration, if I am not mistaken, right? Big chunk, followed by the ethyl, followed by the methyl. I need to look from underneath. That is R configuration. And then the other carbon atom, the configuration of the other one, it will be, the methyl group will be my lowest priority. So it will be bromine, followed by carbon, carbon, carbon followed by two carbons, carbon followed by two carbons. But this one is longer. So yeah, it will be bromine, rest of the molecule, and then the isopropyl. So this is our configuration. So when the elimination takes place, what will be the structure of my alkene? My alkene will have methyl group pointing to you and isopropyl group pointing to you, right? And then ethyl group pointing away from you and methyl group pointing away from you. So what is the stereochemistry of this product? E or Z? The most important group on this carbon atom is the ethyl, and the most important group on the other carbon here is isopropyl, right? The isopropyl. So the isopropyl and the ethyl, they are in opposite sides. So this one here is the E product. So there I can say the configuration of the starting material, the RR configuration, leads to the formation of the E product. If I had got a different configuration here, let's say if I had the RS configuration, that would have given me the Z product. So that is very, very nice. And then here we have a little the explanation for why is that we have such a requirement of having the so-called antiperiplanar relationship. That means that the hydrogen atom that is being abstracted, the two carbon atoms that will form the future alkene, and the bromine that is departing, all of them, they have to be in the same plane. And ideally, it should be anti, not the syn. The syn is higher in energy, but the anti will give you a lower energy. So that's why that will lead to the formation, preferentially to the formation of the alkene when you have an anti-periplanar relationship between the hydrogen and the halogen that is departing. Here we have yet one more example. So here we have this compound where we have the phenyl group here, that is a phenyl group, and that is the way we abbreviate phenyl. When you have a benzene ring as a substituent, we can abbreviate that as simply PH. So there we have a phenyl group, and then here we have another phenyl group. And there you can see that the two phenyl groups are in the same side of the molecule. So once we have abstraction of the proton and departure of the bromine, so then the two phenyl groups will remain in the same side. And then what will be the configuration here in terms of E or Z? Most important group for this particular carbon atom, we have bromine and phenyl. Which one is more important? The bromine. And then in the other carbon atom, which are the most important groups for the other carbon atom? So we have hydrogen and phenyl. Well, obviously the phenyl is more important. And we have bromine and phenyl in opposite sides. So that's why we say this is the E stereoisomer, right? In this next slide, we will start discussing the what happens when you have a ring. So if you have the hydrogen atom that is going to be abstracted and the halogen as part of a ring, so there the situation is a little trickier, right? Because there we need to consider the two conformations of the chair. And you can have two different conformations. In the upper example that we have here, there you can see that the chlorine is in an axial conformation, in an axial position, right? And there is very, very obvious that this chlorine that is axial, it will have two hydrogen atoms that they are antiperiplanar, right? So the two hydrogen atoms that I'm circling here will be appropriate for having elimination E2, right? So either one of them will give me the same product, right? But how about if I have another conformation like this, where the chlorine is in an equatorial position? In an equatorial position, that is bad, right? Because the only group that is antiperiplanar to the chlorine is that carbon-carbon bond. I don't have any hydrogen atom. So elimination E2 will not take place when the chlorine is on an equatorial position. So I will give you a few more examples in the next mini video.